In the second of these talks, I want to talk about polynomials. Polynomials in the frequency response in particular. First, a quick check that everybody knows what a polynomial is. A polynomial is a function of a variable which can be expressed in terms of a sum of different powers of that variable. For example, the function of x, 1 plus x plus 3x squared plus 4x to the power of 5 is a polynomial because it's the sum of a lot of terms, all of which are powers of x. 1 counts as a power of x because I can write 1 as x to the power of 0. Polynomials have some useful and important properties, including the fact that they have roots. And these will turn out to be very important. The roots of a polynomial are the values of the variable, x in this case, where the polynomial evaluates to 0. Possibly the simplest example that everyone will be familiar with will be a quadratic. I could have a polynomial in x, which is x squared plus x minus 6. And I can factorize that to get x minus 2 and x plus 3, which if I multiplied out would give me my polynomial. And if I equate that to 0, I can see that x has the values of 2 or minus 3. Those are the roots of this polynomial. Okay, that's the basics covered. If we have a look at this simple example that we've seen before, you can see that both the numerator and the denominator are polynomials in j omega. And for the more complex example that we've been looking at, this is also true. Both the numerator and the denominator can be expressed in terms of polynomials in j omega. So we're working with j omega as our variable here. We have terms in units, or j omega to the power of 0, terms in j omega, terms in j omega squared, and if we had more complicated circuits, we may get terms in j omega cubed, j omega to the power of 4, and so on. What I haven't proved, but does turn out to be true, is that for any circuit that we can build with resistors, capacitors, and inductors, we can always express the frequency response in terms of the ratio of two polynomials in j omega. So we could write a general form for the frequency response of any such circuit, like this. The ratio of one polynomial in j omega with coefficients a0, a1, a2, and so on, to another polynomial in j omega with coefficients b0, b1, b2, and so on. As we've noted, polynomials have roots, values where the polynomial evaluates to 0. And we can express these polynomials in terms of their roots in this form here. If I multiply out all of these brackets, the term in j omega to the power of n, where n is the number of roots that they have, would just be an times j omega to the power of n, which is this term here. The term without any j omegas in it at all would be an times minus z0 times minus z1 times minus z2 and so on, and that would be the term a0, and all of the other terms would have their corresponding coefficients. If I do a simple example, supposing I had on the numerator 1 plus j omega rc, then this polynomial has roots where it evaluates to 0, and that would be where j omega equals minus 1 over rc. So I could write it in the form j omega plus 1 over rc, and then multiply that by rc. And that's just a bit of algebra on this expression here. But we've now written it in a form where it's very easy to see what the roots are. In terms of the notation on the slide, the RC would be the AN, and the Z0 would be minus 1 over RC. Now, I've chosen to use Z for the roots of the numerator and P for the roots of the denominator, because these are what we mean by zeros and poles. And this is the technique that we use to simplify how we describe frequency responses. Rather than specifying them in terms of the coefficients of j omega and j omega squared and so on, we specify them in terms of the roots of these polynomials. And the roots of the numerator we call the zeros, and the roots of the denominator we call the poles. There are just a couple of slight complications to be aware of. The first is that some of the roots of the numerator polynomial can, and often are, at 0. That means that the term a0 might be 0, the term a1 may be 0 as well. If this happens, then the numerator can be written something like this. 3j omega cubed plus and so on up to the maximum power of j omega that appears in the numerator. And we can therefore extract the value of, in this case, j omega squared from all of these terms and just write j omega squared times a2 plus a3 j omega plus and so on up to an j omega, oops, that should have been an n, j omega to the power of n minus 2. And this is what we would commonly do. So our expression would turn into this standard form, where we've extracted this value of j omega to the power of, in the general case, capital N, where capital N is the number of roots that the polynomial has at 0. And that leaves us with a simpler polynomial to solve to find the other roots of the polynomial. The second slight complication might look a little bit odd at first sight. I'm going to take all of these terms in the factorized form of the numerator and denominator polynomials, things like j omega minus zn, and I'm going to extract a factor of minus zn from both terms. So that would give me minus zn outside the bracket, and j omega divided by minus zn minus zn divided by minus zn inside the bracket. Well, zn, or minus zn divided by minus zn, is just 1. And j omega over minus zn is just going to be j omega over minus zn. So I will get this, which is equal to this. I've just written it in a slightly odd way. I'm now going to take all of these factors of minus the roots that are extracted from all of these factors and combine them into one big term at the beginning of the expression there. And I'm going to call this term here g. It's equal to an times the product of minus all of the roots of the numerator polynomial, and so on, divided by bn times the product of minus all of the roots of the denominator polynomial, in other words, the poles. And that leaves me with this expression here, which I can simplify to this. So this is the expression that we're going to be working with. The frequency response, h of omega, is g, where g is just given by this, but we're never going to calculate it like this. It's just going to be g, a gain factor, times j omega to the power of n, where n is the number of roots of the numerator that occur at j omega equals 0, or if you like, the number of factors of j omega that you can extract from all of the terms in the numerator polynomial, times terms that look like this. J omega over minus Zn, J omega 1 plus J omega over minus Zn plus 1, and so on the numerator, and 1 plus J omega over minus P0, 1 plus J omega over minus P1, and so on the denominator. And at this stage, you might be asking yourself, why am I writing 1 plus J omega over minus P0? Wouldn't it be easier to write 1 minus J omega over P0? And the reason that I'm writing things in this form is that when we actually calculate the value of these poles, they will almost always be negative. So minus P0 is actually a positive number. We'll see why that is and what it implies in the videos coming up. That's all for this time. Next time I want to start looking at some of the terms in this general form here in a bit more detail.